In this lecture we'll answer on two questions. In the first question, we find out the area of this circle that is inside square ABCD, and in the second question, we find out the green area that is actually inside a quarter circle. Okay, so we start with the first question. In the drawing, we have square ABCD. You know that angle CBT equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle that is inside square ABCD. Okay, so first of all, we'll define the center of this circle as O. And we will join points O and P together by a straight line. Point O is the center of the circle, point P is the point on the circle itself, therefore OP is the radius of this circle that we will define as R. And we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees. And this angle will be also equal to 90 degrees. In the next step, we will join points O and Q together by a straight line. Again, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that is equal to R. Okay. We also know that all the angles inside the square ABCD are right angles. So this angle is a right angle. This angle, it is also a right angle. This is also a right angle. This angle, it is also a right angle, it is equal to 90 degrees. So inside quadrilateral AQPO, but before that, we have the radius OQ that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So, actually, inside quadrilateral POAQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So this angle must be equal to 90 degrees, equals 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. So we found out that inside quadrilateral AQPO we have 4 right angles. Therefore quadrilateral AQPO is a rectangle. So I write it down. Quadrilateral AQPO it is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AQ equals to side PO. AQ equals to PO. But we have already found out that PO equals to R, it is the radius of the circle. And from this equation AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side AP equals to side QO. AP equals to QO, but QO equals to R, it is the radius of the circle. And for this equation AP equals to QO equals to R, we will derive that AP is also equals to R. AP equals to R. Here AP equals to R. So we actually found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. So I write it down, quadrilateral AQPO is a square. Okay. We also know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. In square ABCD, we know that side AD equals to side AB. AD equals to AB. What is the value of AD? AD equals to R plus 5. And what is the value of AB? The length of AB is R plus QB. So in conclusion, we found out that R plus 5 equals to R plus QB. We will subtract R from this equation and we get that R will get cancelled and we get that 5 equals to QB, or QB equals to 5 units. Here QB equals to 5 units. In the next step I present to you rule number 2 and we will implement rule number 2 in our drawing. So actually, according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing. Why? Because in our drawing, we'll focus on the common external point B. Here we'll focus on the common external point B. From the common external point B, we have two tangents to this circle. I'll repeat again. For the common external point B, we have two tangents to this circle. We have tangent BQ, and we also have tangent BS. And according to rule number 2, the lengths of those two tangents must be equal to each other. Repeat again. If we focus on the common external point B, we have two tangents from point B, tangent BQ and tangent BS, and according to rule number 2, they must be equal to each other. So BQ equals to BS, but we have already found out that BQ equals to 5 units. Here BQ or QB equals to 5 units. So we can write here that BQ equals to 5 units. And from this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5 units. BS equals to 5 units. Now we found out that BS equals to 5 units. What is the size of angle QBS? What is the size of this angle? The size of this angle must be equal to angle ABC, the big angle that is equal to 90 degrees, minus this angle that is equal to 30 degrees. So in conclusion, we found out that the size of angle QBS equals to 90 degrees minus 30 degrees, that is 60 degrees. In the next step, we join points Q and S together by a straight line. Here we created triangle QBS. In triangle QBS, side is BS equals to side BQ. They are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that also must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, because of the fact that those two angles that are located in front of equal sides must be equal to each other. So both those two angles are equal to alpha. This angle equals to 60 degrees. Therefore, the sum of the other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha equals to 120 degrees. I will write it down. So we found out actually that alpha plus alpha equals to 120 degrees in triangle QBS. Alpha plus alpha is 2 alpha, so 2 alpha equals to 120 degrees. Here we divide this equation by 2, and we get that angle alpha equals to 120 degrees over 2 is 60 degrees. So we found out that this angle alpha equals to 60 degrees. And this this is also angle alpha that is equal to 60 degrees. So actually we found out that inside triangle SPQ we have three angles that equal to 60 degrees. Therefore, triangle QSB is an equilateral triangle. So I write it down. Triangle QBS is an equilateral triangle. Why? Because it has three angles that are equal to 60 degrees. And we know that in any equilateral triangle, all the sides are equal to each other, and especially this equilateral triangle. So QB equals to 5, SB equals to 5, therefore QS must be also equal to 5 units. QS equals to 5. We join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. And we have the radius OS that is drawn to the point of tendency, therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so in the next step, I will copy quadrilateral SOQB in a new page and we'll analyze quadrilateral SOQB. So actually, this is quadrilateral QBOS that I covered from the original drawing. You know that the sum of the angles in any quadrilateral is 360 degrees. Therefore, the size of the missing angle must be equal to 360 degrees minus the sum of the two other three angles. So I write it down. The size of the missing angle, that is actually angle QOC, must be equal to 360 degrees minus the sum of the three other angles. That is to say, it is 90 degrees plus 90 degrees plus 60 degrees. So the size of angle, the missing angle QOC is equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So in conclusion, I found out that the size of the missing angle QOC equals to 360 degrees minus 240 degrees, it is 120 degrees. So this, the missing angle, equals to 120 degrees. So I can write here in the drawing that this angle equals to 120 degrees. In the next step, I present to you the law of cosines, and we'll implement the law of cosines in the green triangle QOS. So actually, the law of cosines is true in any triangle. So if we have triangle ABC that could be any triangle, so this is triangle ABC. We know that side AB for triangle ABC equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. And the angle between side AB and side AC is theta. Then, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I repeat again, according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. You can actually implement the law of cosines in the green triangle QOS. So you copy triangle QOS in this new page, and we implement the law of cosines in the green triangle QOS. So actually, this is triangle QOS, the copy from the original drawing. So according to the law of cosines, we get that 5 squared equals to R squared plus R squared minus 2 times R times R times cosine 120 degrees. Repeat again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, that is equal to R squared plus R squared is 2R squared, minus 2 times R is minus 2R squared, times cosine 120 degrees. Cosine 120 degrees is minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. minus times minus is plus. So in conclusion we get that 25 equals to 2r squared plus r squared, or 25 is equal to 2r squared plus r squared is 3r squared. Here we divide this equation by 3 and we get that r squared equals to 25 over 3. And we know that the area of any circle is equal to pi r squared, and especially the area of our circle, it will be equal to pi r squared. So, but we have already found out that r squared equals to 25 over 3, therefore we substitute r squared in this formula by 25 over 3. So in conclusion we found out that the area of our circle, it is equal to either 25 pi over 3 square units, or in terms of numbers is equal to 50.265 square units. Okay, so we finished in the first question. In the next step I will present to you the second question, and we will solve the second question in 3 different methods. So in the drawing we have a quarter circle. Inside the quarter circle we have a small circle. We know that line 7 CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the green area. So we'll start with the first method, and we will define the center of the small circle as J. We define the point of tendency CD with the small circle as E. We define the point of tendency OB with the small circle as F. We join points J and E together by a straight line. Point J is the center of the small circle, point E is the point of the circle itself, therefore JE is the radius of the small circle that we will define as R. We have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we join points J and F together by a straight line. Again, point J is the center of the circle, point F is the point of the circle itself, therefore JF is the radius of this circle that is equal to R. Again, we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that this is a quarter circle, therefore point O is the center of the quarter circle, and this angle must be equal to 90 degrees. And also here AO must be the radius of the quarter circle that we define as capital R. So here the radius AO, as a radius it must be a straight line. So we know that AO is a straight line, so if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AO at point C, we have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 3. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay, in the next step, from the center of the small circle, that is to say from point J, we draw perpendicular on CO. So here, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. So actually, inside quadrilateral CE, we define the touching point of the perpendicular from point J and CO as T. So actually inside quadrilateral CETJ, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And inside quadrilateral TOFJ, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So we actually found out that angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle EJF equals to 180 degrees, and therefore angle EJF is a straight line. Any angle that is equal to 180 degrees must be a straight line. So it is a straight line. And if angle EJF is a straight line, then line segment EJF is a straight line. And if line segment EJF is a straight line, then line segment EF is also a straight line. Line segment EF is a straight line. If line segment EF is a straight line, then it means that quadrilateral CEOF is a rectangle. I write it down here. Quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF, rectangle CEOF. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Here CO equals to 2R. In the next step, we will join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. So on the right green triangle, triangle OCD, by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. The hypotenuse in the right triangle COD is OD. Therefore, the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO squared plus CD squared. CO squared plus CD square. So in conclusion, I found out that only equation number 1, all D square equals to CO square plus CD square. OD is the radius of the quarter circle that is equal to capital R, therefore OD square will be equal to capital R square, and it is equal to CO square. CO equals to 2R, therefore CO square will be equal to 2R square, that is 4R square, plus CD square. CD equals to 8 units according to what is given as the equation, therefore CD square will be equal to 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. Here we subtract 4R square from this equation number 1, and again that according to equation number 1, capital R square minus 4R square equals to 64. So we found out that according to equation number 1, capital R square minus 4R square equals to 64. And what is actually the area of the green shape? The area of the green shape, it is very easy to see from the drawing that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area that we are looking for, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. So, and the area of the quarter circle will be equal to pi times capital R square over 4 minus the area of the small circle, that is pi R square. So here we take pi over 4 as a common factor out of those two expressions. So pi over 4 is a common factor. What is left from pi times capital R square over 4, so we took from it pi over 4 is a common factor. What is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 is a common factor. What is left is actually minus 4 times pi R, 4 times R square. Why? Because 4 times R square times pi over 4 equals exactly to minus pi R square. But we have already found out that capital R square minus 4R square equals to 64. Therefore, we substitute capital R square minus 4R square by 64, and we'll get that the area of the green shape equals to pi over 4 times 64. And here 64 over 4 is 16, so in total this expression equals to 16 pi, or in terms of numbers, the area of the green shape will be equal to 50.265 square units. Okay, so we finished the first method. In the next step, I'll present to you the second method to find out the area of the green shape. Okay, so actually in the second method we'll use before the fix that we have already found out in the first method. We have already found out that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. And here, what is the value of AC? From the drawing it is very easy to see that AC equals to AO minus CO. Again, AC equals to AO minus CO. So it is AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, AC equals to capital R minus 2R. We have already found out in the first method that this angle equals to 90 degrees. This angle it is also equals to 90 degrees. This is the radius of the small circle. This is also the radius of the small circle. In the next step, we complete the quarter circle to a circle. So we completed the quarter circle to a circle. We will extend the radius AO until it touches the circle. And we will define the touching point of the extended radius AO and the circle as point T. And we will extend the straight line DC by straight line until it intersects with the circle. We will define the touching point of the extended DC and the circle as point M. We will join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the big circle that is equal to capital R. We will join points O and D together by a straight line. So here point O is the center of the big circle, point D is the point of the big circle itself, therefore OB is the radius of the big circle that is equal to capital R. Okay, here DC is a straight line, and then we extended the straight line DC by a straight line. And when you extend the straight line by a straight line, the result must be a straight line. So the result that is DM must be also a straight line. So we know that DM is a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of MD at point C? This angle, we have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to rule number 3. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of MD at point C to 180 degrees. This angle must be also equal to 90 degrees. So we have here two right triangles, triangle MDC and triangle CDO, triangle OCM and triangle CDO. In the next step, we will prove that those two right triangles can go into each other. Okay, so we have triangle the right triangle, triangle COM, the right triangle, triangle DOC. So why those two right triangles can go into each other? First of all, side CO is a common side that belongs to both triangles. So CO equals to CO equals to itself as a common side that belongs to both triangles. In addition, MO equals to OD, they are both the radii of the circle, therefore they are equal to each other. So MO equals to OD equals to capital R. So actually, by proving that the hypotenuse and one perpendicular of those two right triangles congruent, we've actually proved that those two right triangles can go into each other. Why? I'll explain you why. Because if, for example, we have two right triangles, we have the right triangle, triangle ABC. This is the right triangle, triangle ABC. And we also have right triangle, triangle DEF. Okay, and you know that the hypotenuse of those two right triangles congruent, and also they congruent if one perpendicular. Here, the hypotenuse DF equals to the hypotenuse AC equals to 5 units, and the perpendicular AB equals to the perpendicular DE, they are both equal to 4 units. So therefore, the third side BC must also congruent. Why? Because the third side, according to the Pythagoras theorem, will be equal to the square root of 5 square minus 4 square. 5 square is 25 minus 4 square, that is 16. 25 minus 16 is 9, and the square root of 9 is 3. Here also EF will be also equal to the square root of 5 square minus 4 square, that is 3. So we actually found out that if we have in two right triangles perpendicular and one and the hypotenuse and one perpendicular congruent in those two right triangles, then the third side also congruent. Therefore, the two right triangles will be congruent to each other according to side rule. Here we proved that the hypotenuse and one perpendicular congruent in those two right triangles. Therefore, those two right triangles will be congruent to each other according to side rule. Okay? So I write it down. We actually found out that the right triangle, triangle COM, congruent to the right triangle, triangle DOC, according to side rule. And from the fact that the two right triangles can go into each other, we will derive that side DC congruent is equal to side CM. DC equals to CM. DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say DC and CM, must be also equal to each other. But it is given as the equation that DC equals to 8 units. And from this equation, 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. CM equals to 8 units. Here, CM equals to 8 units. Okay, here point O is the center of the big circle, point T is the point on the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. In the next step I present to you rule number 11 and we will implement rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Point C is the intersection point of chord AT with chord MD. So I write it down. We have chord AT intersects with chord MD at point C. Point C is the intersection point. Therefore, according to rule number 11, we'll get that MC times CD equals to AC times CT. I'll repeat again. Chord AT intersects with chord M with chord M. Chord AT intersects with chord MD. Chord MD at point C. Again, chord AT intersects with chord MD at point C. Therefore, according to rule number 11, MC times CD equals to AC times CT. Okay. MC is 8, CD is 8, so MC times CD is 8 times 8 is 64, and it is equal to AC. AC equals to capital R minus 2R. Times CT. What is the value of CT? CT equals to 2R plus capital R. So we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. So that is to say 64 equals to capital R plus 2R times capital R minus 2R. Capital R plus 2R minus capital R times capital R minus 2R, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. So in our specific expression, A equals to capital R, B equals to 2R, and therefore we get that here 64 equals to, this expression must be equal to A squared minus B squared. A is capital R, therefore A squared is capital R squared minus B squared. B is 2R, therefore minus B squared will be equal to minus 2R squared. So in conclusion, we found out that 64 equals to capital R square minus 2R square. That is to say, 64 equals to capital R square minus 2R square is minus 4R square. So in conclusion, we found out that 64 equals to capital R square minus 4R square. Okay. But what is actually the area of the green shape? The area of the green shape is actually equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle is equal to pi R square. Here we took pi over 4 as a common factor out of those two expressions, and we have already found out that inside the brackets what is left is capital R square minus 4R square. Okay, but we have already found out that capital R square minus 4R square equals to 64. Okay, so you can substitute capital R square minus 4R square by 64. We'll do it now, we get that this expression in total equals to pi over 4 times 64. That is to say, the area of the green shape equals to 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Next step, I present to you how to find out the area of this green shape according to the third method. We have already found out in the first method that CO equals to 2R, AO is equal to capital R, and AC equals to capital R minus 2R. We have already found out that this angle equals to 90 degrees. This angle, it is also equals to 90 degrees. This is the radius of the small circle. This is also the radius of the small circle. In the next step, we'll complete the quarter circle to a semicircle. We'll extend the radius AO by a straight line until it intersects with the semicircle. We'll define the touching point as point between the extended radius AO and the semicircle as T. So point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle that is equal to capital R. We actually extended the radius AO, that is a straight line, by a straight line. When you extend a straight line by a straight line, the result must be a straight line. Therefore, AT is a straight line. And because of the fact that AT is a straight line, AT, it is actually a chord in this semicircle. So AT is a chord in this semicircle that is equal to 2R, 2 times capital R, and it passes through the center of the semicircle. Therefore, AT must be the diameter of the semicircle. AT is the diameter of the semicircle, because of the fact that any chord that passes through the diameter of the semicircle and it is equal to 2 times capital R must be the diameter of the semicircle. So AT is the diameter of the semicircle. In the next step, we'll join points B and T together by straight. We'll join points D and T together by straight line. And we'll join points A and D together by straight line. Here we created peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of the semicircle. Repeat again, peripheral angle ADT rests on AT, that is the diameter of the semicircle. And we actually have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or a semicircle must be equal to 90 degrees. Here we have peripheral angle AMB that rests on AB, that is the diameter of this circle. Therefore, peripheral angle AB equals to 90 degrees according to this rule, rule number 5. We can actually implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, according to rule number 5, peripheral angle ADT must be equal to 90 degrees. Okay. In the next step, we'll define angle ATD as alpha, and we'll define angle TAD as beta. We'll focus on the right triangle, triangle ADT. In the right triangle ADT, this angle equals to 90 degrees. Therefore, the other two angles, the sum of the other two angles, must be also equal to 90 degrees. In order to complete the sum of the angles in this right triangle to 180 degrees, the other two angles must be also equal. The sum of the other two angles must be equal to 90 degrees. That is to say, alpha plus beta must be equal to 90 degrees. Alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. Here we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. Okay, now we'll focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, this angle equals to 90 degrees. This angle equals to beta. Therefore, the missing angle here must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees it is 180 degrees. That is the sum of the angles in any triangle. So this angle equals to 90 degrees minus beta, but we have already found out that 90 degrees minus beta equals to alpha. So we can substitute this angle that is equal to 90 degrees minus beta by alpha. Likewise, we focus on the right triangle, triangle CDT. This right triangle CDT, this angle equals to alpha. Therefore, this angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta. So we can substitute this angle that is equal to 90 degrees minus alpha by beta. In the next step, we'll prove that the right triangle, triangle ACD, the right green triangle, triangle ACD is similar to the right triangle, triangle CDT. Okay, so why those two right triangles are similar to each other? The right triangle, triangle ACD, the right green triangle is similar to the right triangle, triangle DCT. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So I write it down. Angle ADC equals to this angle that is actually angle CTD. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD, and it is equal to this angle that is actually angle CDT. So they are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ACD, that is equal to this angle, that is angle DCT. So they are both equal to 90 degrees, therefore they are equal to each other. So we actually found out that the two right triangles are similar to each other according to angle similarity rule. So I write it down. Triangle ACD is similar to triangle DCT according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that AC in triangle ACD over CD in triangle CDT is equal to CD in triangle ACD over CT in triangle DCT. Repeat again, we will derive that AC over CD equals to CD over CT. AC equals to capital R minus 2R, CD equals to 8, and CT equals to 2R plus capital R. So in conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here, We cross multiply this equation number 1, and we get that 8 times 8 is 64. That is equal to capital R plus 2R times capital R minus 2R. So according to equation number 1, 64 equals to, and we have already found out that capital R plus 2R times capital R minus 2R equals to capital R squared minus 4R squared. Minus 4R squared. So according to equation number 1, we found out that 64 equals to capital R squared minus 4R squared. But what is actually the area of the grain shape? The area of the grain shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the grain shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4, and the area of the small circle equals to pi R squared. Here we took pi over 4 as a common factor out of this two expressions, so inside the brackets we left only with capital R squared here minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64, so we can substitute capital R squared minus 4R squared in this equation by 64. We'll do it now, and we get that the area of the grain shape equals to pi over 4 times 64. So 64 over 4 is 16, so this expression in total equals to 16 pi. That is to say, the area of the grain shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. So we finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. This angle CBT equals to 30 degrees. Line segment PD equals to 5 units, and our mission is to find out the area of this circle. Okay, so first of all, we define the center of the circle as O. Here, PO is the radius of the circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, OQ is the radius of the circle that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle equals to 90 degrees. We know that all the angles inside the square are right angles, so all the angles inside square ABCD are right angles. So those 4 angles are all right angles. Especially this angle, it is a right angle. So inside quadrilateral AQPO, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrilateral AQPO, we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we have already found out that PO equals to R. And from this equation, AQ equals to PO equals to R, we will derive that AQ equals to also to R. Here AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that QO equals to AP. But we have already found out that Q equals to R. And from this equation, AP equals to QO equals to R, we will derive that AP is also equals to R. Here AP equals to R also. So we actually found out that quadrilateral AQPO is not a rectangle but a square because all of its sides are equal to each other, they are equal to R. We also know that all the sides of square ABCD are equal to each other. That is to say, side DA equals to side AB. Here, AD equals to AB. AD equals to 5 plus R, AB equals to R plus QB. That is to say, R plus 5 equals to R plus QB. We subtracted R from this equation and found out that QB equals to 5 units. Here, QB equals to 5 units. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. We have the common extreme point P. From the common extreme point P, we have two tangents to the circle. Tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing because in our drawing we have the common extreme point B. From the common extreme point B, we have two tangents to the circle. Tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS. Here, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5. So from this equation, 5 equals to BQ equals to BS, we derive that BS is also equals to 5 units. Here, BS equals to 5 units. Then, what is the size of this angle? This angle equals to 90 degrees minus 30 degrees, that is 60 degrees. The joint points S and Q together by straight line. In this way, we created triangle SBQ. In triangle SBQ, QB equals to BS equals to 5 units. So, in front of those equal sides, in triangle QBS, we have equal angles. So, those two angles that are located in front of equal sides must be equal to each other. So, if one angle is alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. So those two angles, they are both equal to alpha. This angle equals to 60 degrees, therefore the sum of the other two angles must be equal to 180 degrees and 60 degrees, that is 120 degrees. That is to say, we found out that alpha plus alpha, it must be equal in total to 120 degrees. So alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that alpha equals to 120 degrees over 2 is 60 degrees. So, inside quadrilateral QBS, alpha equals to 60 degrees, those two angles are equal to 60 degrees. This angle also equals to 60 degrees, so we have three angles that are all equal to 60 degrees, therefore triangle QBS is an equilateral triangle. Repeat again, triangle QBS is an equilateral triangle because it has three angles that are all equal to 60 degrees. And we know that in an equilateral triangle, all the angles are equal to each other. All the sides are equal to each other. So QB equals to 5, PS equals to 5, therefore QS must be also equal to 5. Here, QS equals to 5. Okay, then we actually joined points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. I copied quadrilateral OSBQ in the new page and analyze triangle quadrilateral QBOS. This is quadrilateral QBOS that I copied here. In quadrilateral QBS, those two angles are equal to 90 degrees, this angle equals to 60 degrees, and this is the missing angle. We know that in any quadrilateral, the sum of the angles is equal to 360 degrees. Therefore, 360 degrees minus the sum of those three angles must be equal to the missing angle. So the missing angle, that is angle QOC, must be equal to 360 degrees minus the sum of those three angles, that is 90 degrees plus 90 degrees plus 60 degrees. 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So we found out that the missing angle QOC equals to 360 degrees minus 240 degrees, that is 120 degrees. So the missing angle here equals to 120 degrees. This is the missing angle, the QOC, that is equal to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in this green triangle, triangle QOS. According to the law of cosines that is true in any triangle, if we have this triangle ABC that could be any triangle, side AB equals to A units, side AC equals to B units in its length, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented the law of cosines in this triangle, triangle QOS. In this triangle, triangle QOS, according to the law of cosines, we get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25. R squared plus R squared is 2R squared. And we have minus 2R times R is minus 2R squared. Cosine 120 degrees is minus 1/2. Here we have 2 in the denominator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in conclusion, found out that 25 equals to 2R squared plus R squared. 2R squared plus R squared is 3R squared. So 25 equals to 3R squared. We divided this equation by 3 and found out that R squared equals to 25 over 3. We know that the area of any circle is pi r squared, and especially in the area of our circle, it will be equal to pi r squared. But we have already found out that r squared equals to 25 over 3, therefore we can substitute r squared in this equation by 25 over 3. We did it, and we got that the area of our circle will be equal to pi times r squared. R squared is 25 over 3. So we found out that the area of our circle is equal to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first question. Then I presented to you the first question, and we solved the first question in 3 different methods. So in the drawing, we have a quarter circle, inside the quarter circle we have a small circle. We know that line segment CD equals to 8 units. Angle ACD equals to 90 degrees, and our mission is to find out the value of the green area. So we define the center of the small circle as J. JE is the radius, and JF is the radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees. JE is the radius that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In any quarter circle, this angle equals to 90 degrees, and point O is the center of the quarter circle. AO is the radius. Because of the fact that this is a quarter circle, AO must be the radius of the quarter circle that we define as capital R. So, if we focus on this side of the straight line AO is a radius, it must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals 90 degrees. Therefore the missing angle must be equal to 90 degrees in order to complete the sum of the angles in this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. Okay. Then from point J we go perpendicular on CO. We define the touching point of the perpendicular from point J and CO is T. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. In quadrilateral CETJ we have 1, 2, 3 right angles. We have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. In quadrilateral TJOF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So angle EJF, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. Therefore angle EJF is a straight line. If angle EJF is a straight line, it means that EJF is a straight line, and if EJF is a straight line, it means that EF is a straight line, and if EF is a straight line, it means that quadrilateral CEOF is a rectangle. Quadrilateral CEOF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to OF. Quadrilateral CEOF, CO equals to EF. CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. So we can write here that EF equals to 2R. And for this equation, CO equals to EF equals to 2R, we derive that CO is also equals to 2R. Yes, CO equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right triangle, triangle COD. According to the Pythagoras theorem, the right triangle, triangle COD, OD square equals to CO square plus CD square. Again, OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square. CO equals to 2R, therefore CO square is 4R square. CD equals to 8, so CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. We subtracted 4R square from this equation, equation number 1, we found out that capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4. And the area of the small circle is pi R square. Then we took pi over 4 as a common factor out of those two expressions. What is left from pi times capital R square over 4 out of the 2 form it pi over 4 as a common factor. What is left is actually capital R square. And what is left from minus pi R square after we form it pi over 4 as a common factor? What is left is actually minus 4R square, because minus 4R square times pi over 4 equals to minus pi R square. Here we already found out that capital R square minus 4R square equals to 64. Therefore we can substitute capital R square minus 4R square by 64. We did it and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the first method, then I presented to you the second method. In the second method we used with all the things that we have already found out in the first method. We have already found out that CO in the first method, that CO equals to 2R, AO equals to capital R, it is the radius of the quarter circle. And what is the value of AC? AC equals to AO times CO. Again, AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. We extended the radius AO by a straight line until it touches the circle at point T. Point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle, that is equal to capital R. Then we extended the straight line CD by straight line until it touches the circle at point M. When you extend the straight line by straight line, the result is a straight line. So MD, it must be also a straight line. If we focus on the lower side of the straight line MD at point C, here the sum of the angles must be equal to 180 degrees. So each angle we have here, this angle equals 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the lower side of MD at point C to 180 degrees, this angle must be equal to 90 degrees. So we created here two right triangles, triangle COD and triangle CMO. We proved that those two right triangles can go into each other. Why they can go into each other? First of all, CO is a common side that belongs to both triangles, so CO equals to itself, and we have OD equals to OM, they are both the radii of the big circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular can go into those two right triangles, we proved that those two right triangles can go into each other. I'm explaining why. Because if we have two right triangles with hypotenuse on one side that can go in, then the first side must also can go in. Here, AC equals to DF equals to 5, and AB equals to DE equals to 4. Therefore, the first side must also can go in, because the first side, according to the Pythagoras theorem, will be equal to the square root of 5 units minus square root of 4 units, minus 5 square minus 4 square. 5 square is 25, 4 square is 16, so 25 minus 16 is 9, and square root of 9 is 3. So we found here that if we have hypotenuse and one perpendicular that can go into two right triangles, then the third side must also can go in. Here, the third side in both the right triangles is equal to 3. Therefore, those two right triangles, we can go into each other according to side rule. From the fact that those two right triangles can go into each other, we derive that DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say CD and CM, must be also equal to each other. But we have only is given as a equation that DC equals to 8 units, and from this equation 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. Here CM equals to 8 units. Okay? So we have only found out that point O is the center of the circle, point T is the point of the circle Z, therefore T is the radius of the big circle that is equal to capital R. Then we implemented rule number 11 in our drawing. What is rule number 11? According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I repeat again. Chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. MC is 8, CD is 8, so 8 times 8 is 64. AC is capital R minus 2R. CT is capital R plus 2R. So we found out that 64 equals to capital R minus 2R times capital R plus 2R. We have already found out that this expression equals to here capital R plus 2R times capital R minus 2R according to the algebraic identity A plus B times A minus B equals to A squared minus B squared. Here in our specific expression A equals to capital R, B equals to 2R. Therefore A squared minus B squared is A is capital R, so A squared is capital R squared minus B squared, B is 2R, so minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say 64 equals to capital R squared minus 4R squared. Okay? So what is the area of the green shape? the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. We took pi over 4 as a common factor, and we have already found out that inside the brackets what is left is capital R square minus 4R square. But we've already found out that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finish with the second method, and I presented to you how to find out the area of the green shape according to the third method. In the third method here, we already found out in the first method that CO equals to 2R. AO is the radius of the quarter circle that is equal to capital R. We have already found out in the second method that AC equals to capital R minus 2R. Then we completed the quarter circle to a semicircle. We extended the radius AO by the straight line until it touches the circle the semicircle at point T. Point O is the center of the semicircle, point T is the point of the semicircle Z, therefore OT is the radius of the semicircle that is equal to capital R. We extended the radius AO by a straight line. When you extend the straight line by a straight line, the result is a straight line. So AT is a straight line that passes for the center of the circle, and it is equal to R. We can see AT as a chord that passes for the center of the semicircle. Any chord that passes for the center of a semicircle must be the diameter of the semicircle. And we know that chord AT equals to 2 times capital R, and it passes for the center of the semicircle, therefore AT is the diameter of the semicircle. Then we join points D and T together by a straight line. We join points D and A together by a straight line. We created here peripheral angle ADT. Peripheral angle ADT rests on AT, that is the diameter of this semicircle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of a circle or a semicircle must be equal to 90 degrees. We have peripheral angle A and B that rests on A and B, that is the diameter of this circle. Therefore, peripheral angle A and B equals to 90 degrees according to this rule, rule number 5. So we can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT equals to 90 degrees according to rule number 5. Then we define this angle as alpha, this angle as beta, and we focus on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the rest of the two other angles in this triangle, triangle ADT, must be equal also to 90 degrees. Because 90 degrees plus 90 degrees, it is 180 degrees. It is the sum of the angles in any triangle. Therefore, alpha plus beta must be equal to 90 degrees. We subtracted alpha from this equation and found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation and found out that alpha equals to 90 degrees minus beta. Okay, then we focused on the right triangle, triangle ACD. In the right triangle, triangle ACD, this angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we have already found out that 90 degrees minus beta equals to alpha, so we can substitute this angle 90 degrees minus beta by alpha. Likewise, in the right triangle DCT, this angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, therefore we substitute 90 degrees minus alpha here by beta. Then we proved that the right green triangle ACD is similar to the right triangle CDT. Triangle CDT is similar to the right triangle ACD. The right green triangle ACD. Why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we derive that AC over CD equals to CD over CT. Again, AC over CD equals to CD over CT. AC is capital R minus 2R, CD is 8, and CT is capital R plus 2R. Because we multiply this equation number 1, we found out that 8 times 8 is 64 equals to capital R plus 2R times capital R minus 2R. And we already found out that this expression equals to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. And what is actually the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So we have already found out that the area of the quarter circle equals to pi times capital R square over 4, and the area of the small circle equals to pi R square. We took pi over 4 as a common factor out of those two expressions, and inside the brackets we left only with capital R square minus 4R square, but we have only found out that capital R square minus 4R square equals to 64. So we can substitute capital R square minus 4R square here by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So in all three methods we found that the area of this green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, thank you very much.